Good afternoon, everyone, and welcome to this talk, Does the Everyday World Really Obey Quantum Mechanics? By Professor Anthony Leggett, whom we are very honored to host at the Asia Research Institute. As you will get a more thorough introduction of Professor Leggett from my colleague, A.R. Bala, and my job here now is basically to introduce the Asia Research Institute. Some of you may be wondering why should we be sponsoring this talk on physics, even if it is the physics of the everyday world.
Thank you, Prof. Dwara. And now, ladies and gentlemen, I think, I should also expand a bit on why we invited Professor Anthony Leggett to give a talk in an institute or hosted by an institute that is largely confined to work in the social sciences and humanities. But before I do that, I would also like to introduce Professor Leggett, a bit more, because some of you, are not in the area of physics, may not be too familiar with his work or his achievements. He's a world authority in low-temperature physics, and he was awarded the Nobel Prize in Physics in 2003 for his path-breaking work in the theory of superfluidity. Currently, he is the John D. and Catherine T. MacArthur Professor and Center for Advanced Study Professor of Physics at the University of Illinois at Urbana-Champaign. He is a member of many of the world's great academic societies, and I can't list all of them, including the National Academy of Sciences, the American Academy of Arts and Sciences, the Russian Academy of Sciences, and also a fellow of the Royal Society of the United Kingdom. And for his services in physics, he was also knighted by Queen Elizabeth II in 2004. But now I would like to expand a bit more on the motivation for inviting him. I think he is particularly well placed to talk to an audience such as you, composed of scholars and students from not only the natural sciences, but also the humanities and social sciences. Indeed, it might be surprising to many of you to discover that his first undergraduate qualification led to an Oxford Greats degree, I hope I'm right here, which combined study of Greek and Latin literary classics, ancient history, and philosophy. It was only after that he decided to pursue a second degree in physics, the discipline that led to his Nobel Prize, but one in which his work continues to retain, I think, significant traces of his passion for the humanities and philosophy. It is my great privilege and honor to invite Professor Anthony Leggett to let us know, I think, how we may discover by experiment the answer to the philosophical question up there: does the everyday world really obey quantum mechanics? Sir Anthony Leggett.
Well, it's a great pleasure to be back in Singapore, and I'm very grateful to Bala for organising this talk for me. If we look at the current state of physics as we go into the 21st century, then I think that with the possible exception of cosmology, you would say that physics is almost the paradigm of what the historian and philosopher of science, Thomas Kuhn, calls normal science. That is, it's a subject in which the kinds of questions you're allowed to ask, the kinds of answers you're supposed to give to them, and the kinds of evidence you're allowed to adduce in favour of those answers are all pretty much a matter of agreement among the relevant community. Therefore, you might suppose that fundamental issues in physics would not lead to the sort of intense emotional involvement which we often find in debates, say, about politics or the social sciences. And yet, there is one issue in physics which leads to just these high emotions. And when I was young and mischievous, I used to sometimes go to cocktail parties at physics conferences and so forth, and lob this issue like a hand grenade into a bunch of unsuspecting physicists and stand back to watch the results, which were often quite spectacular, and in one or two cases almost led to blood on the floor. Not quite, luckily. So what is this issue which generates such high passions? Well, in the middle and late 20s, physicists, having spectacularly failed to understand the behaviour of matter at the atomic level in terms of what we now think of as classical physics, came up with what's not really just a new theory, but a whole new way of looking at the world. The way of looking at the world that we call quantum mechanics. Over the past 85 years or so, quantum mechanics has actually been successful beyond its founders' wildest dreams. Just about everything we know at the level of atoms and subatomic physics, and quite a lot of what we know at more macroscopic, towards the more macroscopic level. For example, in chemistry and even nowadays in biology, is really rather well explained by quantum mechanics. And so you might think that really there's no problem there. Unless there is. It turns out that the description which quantum mechanics gives of matter at the atomic level is in many ways very bizarre and very, very divorced from our ordinary ways of thinking. Now, macroscopic matter like this and this and even this is, we believe, made up of atoms and molecules. So if, in some sense, quantum mechanics describes the atoms and molecules rather well, shouldn't it, at least in principle, describe these macroscopic everyday objects just as well? But if we do try to apply quantum mechanics at this, I'll use the word, incidentally, macroscopic very frequently in this talk. It basically means at the everyday level, the sort of level of our direct conscious perception, and so forth. If we do try to bring the quantum mechanical description up to the macroscopic level, we seem to get some very bizarre consequences indeed. Is that a problem? Well, this is where opinions in the physics community differ ferociously. On the one hand, you can find someone like the late Leon Rosenfeld claiming that a particular paper on this topic had basically cleared up all the puzzles and inconsistencies, and now there was no loophole for extravagant speculation. Everything is completely cut and dried. On the other hand, the late Edwin James, quite well-known physicist, actually claimed that the description of the world based on quantum mechanics had, and I think I'm quoting his words correctly, more of the character of medieval necromancy than of science. So indeed, opinions are not only very strongly held, but they're very widely divergent in this field. Now, for many decades, this debate raged backwards and forwards, more or less inconclusively, because I think a lot of physicists regarded the issues as what they called, quote, merely philosophical, unquote. And when physicists say a question is merely philosophical, what they usually mean is that they can't foresee any reasonable experiment bearing on that topic. But over the last 20 or 30 years, things have changed very drastically in this respect. And in fact, a whole new generation of experiments has been done and is beginning to give us at least some insight into this fundamental issue. That's the topic of my talk today. Okay, so what's the problem? Now, for the next few minutes, I am going to ask you to try to follow a little bit of algebra. Hopefully it's rather simple algebra. Don't be scared. If you can't follow it all, don't worry. I'll try to summarise the appropriate conclusions at the end of the day. But I have 4 or 5 slides worth of which do have a little algebra on it. So here's a basic experimental fact. Imagine that we take a set of microscopic objects. They could be atoms, electrons, neutrons, photons, whatever. Let's say for definiteness atoms. Okay, so suppose those atoms start off from some initial state, A, here, and then they can proceed via either path B or path C, and eventually, possibly, end up at E. Of course, they can also end up elsewhere, but we won't be concerned with that. And we arrange that we can, in principle, either decide to inspect which of these two paths is followed for each individual atom, by, say, opening a shutter here. Alternatively, we can close the shutter and refuse to inspect which of these two paths is followed. Now, this is a very general setup. Some of you may be familiar with one instantiation of it, that is the familiar so-called young slits experiment. But it's much more general than that. I could be, for example, be talking about the various possible internal states of the neutral K-meson system. Just a very generic setup. So here, this is how the experiment goes. First of all, we shut off possibility C. How do we do that? Well, we assume that in any particular case, our experimental colleagues know how to do that. For example, if this really were a young slit experiment in which these two were physical slits in an otherwise opaque screen, then all we'd have to do is to block slit C with some opaque object. But we assume that we know how to shut off this possibility. Then any atom which arrives at E must have come through path B. So we're going to measure the probability that we go from A through B to E. And let's call that probability P sub B. Again, we now shut off possibility B, and now the only possibility is to go from A through C to E. Finally, we open both paths, and we measure the total probability that an atom goes from A to E. We call that, perhaps somewhat tendentiously, we're going to call that P sub B or C. We'll see that that is a little question-begging in a way, but we'll see why. Okay, so what's the outcome of this experiment? Well, first of all, let's imagine that we actually inspect each atom to see whether it followed path B or C. Well, then we find, sure enough, each atom does either follow path B or follow path C. And under those conditions, the probability of arrival at E, when both those paths are open, is simply the sum of the probabilities of going through B and the probability of going through C. That's essentially a common sense result. I mean, after all, if there are a number of passengers who are, let us say, travelling from let's say from Chicago to Singapore, and they can come either through Los Angeles or through Frankfurt, then the total number of passengers arriving in Singapore is just going to be the sum of the number who came through Chicago and came through Frankfurt. No big deal, mystery there. Okay. Now here's the surprising bit. Suppose we don't look to inspect which path was followed by any individual atom. Then it turns out that in general, the total probability of arrival when both paths are open is not simply the sum of the probabilities of going through each path separately. In fact, if we set the experiment up carefully, then we can arrange that when only slit B, or only path B is open, then we have a non-zero probability of arriving at E. When only slit C is open, path C is open, a non-zero probability. When we open both paths, however, no particles arrive at E. That's the phenomenon which technically is called total destructive interference. Now, these are, in some sense, the raw experimental facts. What do they suggest? Well, I think they suggest rather strongly that, rather this final result suggests rather strongly that it cannot somehow be the case that each individual atom selected either path B or path C. If that were the case, then, for the sight at least, we should get the common sense result. Now, what positive spin we try to put on this situation, I think, is to a large extent a matter of taste. We could say, for example, that each atom goes through both path B and path C. We could say each atom goes through neither path B nor path C. We could even say that the question really doesn't have much meaning. The one thing that we cannot say, at first sight at least, is that each atom definitely selects either path B or path C. Now, for those of you who know about this, of course, there are some interpretations which try to maintain this, but they have to tie themselves in, to my mind, rather extreme knots in order to do it. So I think this is at least the prima facie conclusion. Okay, as I say, that's the raw data which we're going to be talking about. But now, quantum mechanics does actually give a rather straightforward and simple account of this situation. What quantum mechanics says is that each possible process is represented not exactly by probability, but by something called a probability amplitude, which we'll call A. And that probability amplitude can be either positive or negative. Some of you will know the actual situation is a little more complicated, but I don't want to go into that for the purposes of this talk. It can be, for present purposes, it can be either positive or negative. The total amplitude, to go from A to E, is simply the sum of the amplitudes for the possible paths. That is, for these two paths. And the probability, now remember the probability has to be positive. So that can't just be the amplitude. And in fact, it turns out the probability is the square of the total amplitude. So now let's just do a little more on this. So how does that work? Well, if possibility C is shut off, then the total amplitude, well, the only contribution it has is from path B. And that means that the probability under these conditions, which by our definition is just P sub B, that's simply A sub B squared. If possibility B is shut off, the only possibility is to go through C, so the total amplitude is A sub C. The total probability, which we now call P sub C, under those conditions, is A sub C squared. Now here's the crunch. If both paths are open, then the total amplitude is now the sum of the amplitudes to go through B and C. And that's a very, very generic kind of situation in quantum mechanics. We say that the total amplitude is a superposition, a quantum superposition of the amplitudes to go through path B and path C. Now remember that the total probability, which now by definition is just the P, B or C, that's the total amplitude squared, this squared, well, multiply it up, it gives this plus this. But AB sub B squared is PB, A sub C squared is PC. So P sub B or C is equal to the sum of the P sub B and P sub C. That's just the classical common sense result, plus, crucially, this famous interference term here. And the point I want you to especially notice about this interference term is that to get interference, it has to be the case that A sub B and A sub C must simultaneously exist, whatever exist means exactly in this concept. They must be non-zero for each atom individually. It's not enough to have that somehow non-zero for the whole set of atoms as a whole. It has to be non-zero for each atom. It goes through. One more slide, and then we're done with the algebra, at least for the moment. I'm just repeating this for clarity here. Suppose that for some reason A sub C happens to be plus or minus A sub B at random for the different atoms. Then the average of P sub B or C is given by P sub B plus P sub C plus the average of the interference term. But now the average of this is the average of plus A sub B squared when A sub C is plus A sub B, and minus A sub B squared when it's minus A sub B. And the average of these two, of course, is zero. So, under these conditions, if A sub C is plus or minus A sub B at random, then the interference term just goes away, and we get the common sense result. And the common sense result is exactly what we would have got if we had supposed that each system definitely chose either path B or path C. This, I know this looks a bit, perhaps a little abstract, but that result is important for what we're going on to say. Now, combining what we've already noticed about the raw data with the description that quantum mechanics gives the raw data, it's very natural to reach the following conclusion. When both A sub B and A sub C simultaneously exist, that is, they're simultaneously non-zero, then it's not the case that either path B or path C was selected by each individual atom. Okay? That's a very important conclusion of this first part of the argument. So whenever these amplitudes, as given by quantum mechanics, are non-zero, at least prima facie, not true that one or other of these possibilities is realized. Okay, so far so good. Now, this is rather mysterious, perhaps a state of affairs, and in the early years of quantum mechanics, people agonized a lot about this situation. The person who, in some sense, tried to smooth things down and assure people that there really wasn't much of a problem was the famous Danish physicist Niels Bohr. I think I have him on the next. Yes, here we go. He's on the right here. Very famous physicist. He spent his early years making some very, very important advances in atomic physics and quantum mechanics. But much of his later years he spent in what he called the philosophy of quantum mechanics. And he wrote very voluminously on the subject. And basically he tried to assure people that there was really no problem here. Why not? Well, this is roughly Bohr's attitude rested on two fundamental principles. The first is that microscopic objects, such as atoms or electrons, shouldn't even be thought of as possessing properties in the absence of a specification of the macroscopic, remember that means everyday level, the everyday level apparatus which was going to be used to conduct experiments on them. So, for example, in our original thought experiment, the atom is really in some sense just a link between the initial preparation device, which might be perhaps some kind of oven, and the final detection device, which might be, I don't know, a photographic plate or something like that. And beyond, apart from that, it really in some sense has no real existence. The second principle was that the working of macroscopic apparatus, like counters and various kinds of detector and so forth, had to be described in our ordinary common sense language. In fact, in the language, I think Bohr used the phrase, in the language of classical physics. But when he used that phrase, I don't think he meant you have to use Newtonian mechanics or you have to use Maxwell's electromagnetic theory. I think he just meant you've got to talk about things in our ordinary common sense language in which counters either click or don't click. The pointers either read 5 amps or 10 amps, etc., etc. Not in this funny language of quantum superpositions. So, given, if you were to accept those two postulates, then in some sense the paradox goes away because basically what you say is, well, look, sure, the atom behaves differently depending on whether you observe it or not, but that's not surprising. All the atom is really is, in some sense, a link between different macroscopic experimental setups, and the macroscopic experimental setup is different depending on whether I chose to observe or not observe the atom. And so there's really, in some sense, no paradox. And, well, Niels Bohr's prestige in the physics community was so high that a lot of physicists, I think it's fair to say, basically just accepted his word as gospel and decided, yes, there was no real problem there. But there were always going to be ordinary people around. And in this case, one particular ordinary person was Erwin Schrödinger, who was actually, again, himself a major founding father of quantum mechanics. He was very unhappy with Niels Bohr's solution, and he encapsulated his unhappiness in a famous paper published in 1935. And this is roughly how the paper goes. He said, let's imagine the following, I think he uses the phrase hellish device. You have, again, a system of atoms which start from some initial state A, And they can go, each atom, prima facie, as it were, if we're thinking classically, each atom can either go down path B or through path C. Right? Now, just suppose that we've prepared the atom in such a way that it's bound to go through down path B. Then it just goes away harmlessly and nothing spectacular happens. Suppose, on the other hand, we've prepared our atom. This could be the first one that came out of the gate, as it were. Suppose we've prepared the first atom to come out of the gate in such a way that it's definitely going to go down path C. Then we'll arrange that it goes into some kind of counter here. A certain amount of electronics will work, and as a result of the working of this electronics, a hammer will fall on a bottle of cyanide inside a closed box whose other occupant is a cat, the famous Schrodinger's cat. So if the first atom out of the gate goes down path B, the cat will survive. If it goes down path C, the unfortunate cat will end up dead. Now, incidentally, I would like to point out that my diagram is historically accurate. There is an unfortunate misconception in some quarters that Schrodinger's cat is either shot or electrocuted, but in the original, which is in German, she's very clearly poisoned by a bottle of cyanide. So here it is to show it. So what's the point of this rather bizarre thought experiment? Well, it's a very fundamental feature of quantum mechanics that if an initial state 1 evolves into a final state 1 prime, and an initial state 2 evolves into a final state 2 prime, then the quantum superposition of 1 and 2 must evolve into a superposition of 1 prime and 2 prime. That's a very basic law. I mean, you can challenge it if you like, but if you challenge it, you're no longer doing standard quantum mechanics. You're doing a different kind of theory. So so long as you believe that quantum mechanics is essentially the whole truth, then this is what you have to believe. Now, in this case, the initial state B results in a final state in which the cat is alive. Initial state C results in a final state in which the cat is dead. Now, here comes the crunch. It's perfectly possible, and actually quite easy, to prepare the atom in such a way that its initial state is a quantum superposition of B and C. In other words, the amplitude for B is non-zero, the amplitude for C is non-zero. Then, applying this principle, it follows that the final state now is a quantum superposition of states of the universe, in one of which the cat is alive and well, and in the other of which she's dead. In other words, the amplitude for the cat to be alive is non-zero. Simultaneously, the amplitude for her to be dead is non-zero. Now, you remember that at the microscopic level, we said that whenever you had two amplitudes which were simultaneously non-zero, then you could not interpret that as saying that each system did one thing or the other. So now we've appear to have got the consequence that the poor cat is, in some sense, is neither alive nor dead, but in this quantum superposition of the two states. And yet, now, very fortunately, the animal protection societies have prevented us actually doing this experiment in real life in any statistically significant way, but very few of us, I think, doubt that were we to do it, then when we took the lid off the box, on each occasion, we would see each particular cat to be either definitely alive or definitely dead. In fact, we wouldn't even know how to recognise the quantum superposition. So it's not clear whether this state of affairs is more uncomfortable for the cat or for the theoretical physicist who has to contemplate it. Well, so that's the famous Schrodinger's cat paradox. It was first formulated in 1935, so it's now been around for well over 75 years. And by now there must be thousands, probably tens of thousands of papers in the physics and even in the philosophy literature which have claimed to resolve this paradox in one way or another. So let me just try to give you some kind of feeling for the possible, the kinds of resolution that people have proposed. And I think it's useful at the start to break these up into two really quite different classes of alleged resolution, depending on whether or not it's assumed that quantum mechanics is in principle the complete and universal description of the physical world. Suppose first that you do assume that. Then let me take these slightly out of order here. The first alleged resolution is what I call the extreme statistical, or perhaps nowadays one might say the quantum information theoretic resolution of the problem. And what that basically says is, look, in some sense, this is this line of reasoning is an extension of Niels Bohr's way of thinking. It says, look, you're really taking all this far too seriously. What are these quantum mechanical amplitudes after all? They're merely a recipe for predicting the outcome of various directly experimentally measurable quantities. For example, when I say at the end of the day that the quantum amplitude for my cat to be alive is half, say, and actually 1 over root 2, but that's a detail, and the amplitude for her to be dead, similarly, is equal to that. All I'm really saying is that I have an equal probability of finding her alive or dead. So in other words, it's just really just the amplitudes are nothing more than symbols which allow me to calculate these things. Beyond that, they have no more reality than the recipes which the ancient Chaldeans are said to have used to calculate eclipses. They correspond to nothing whatever in the real world. So there's no problem here. Well, that's I think that solution of the problem does have the virtue of being internally consistent. I mean, if something is nothing more than a recipe, how could it be inconsistent? I mean, the only way in which it could be inconsistent is if different, equally plausible ways of applying it were to give inconsistent results. And I think everyone, including me, is happy that that's not the case with quantum mechanics. But nevertheless, I think it's really very uncomfortable. In the first place, certainly for us physicists who spent many years of our lives learning the formalism of quantum mechanics and learning how to apply it to real-life experiments, really pretty depressing to be told that, well, it doesn't really correspond to anything out there at all. It's just a set of symbols on a piece of paper. But that may be just a psychological problem. I don't know. I think a somewhat more serious problem is that if you really take this interpretation seriously, and I have to back my colleagues against the wall to make them take it seriously, but if they do, then they have to admit that below the level of direct observation, we really have no description of reality at all. So the questions like, what was the state of this particular cat before I took the lid off the box and looked at her? I mean, it's not merely unanswerable, it's really meaningless in some sense. There just was no state of the cat before that. All that I have is my direct conscious observations. And that, I think, makes a lot of people very, very unhappy. However, I would have to admit that if a time traveller were to come back from the year 5000 and tell me that in the year 5000 everyone is still perfectly happy with quantum mechanics and ask me to react, I think I would have to take that point of view. But I don't feel good with it at all. Well, so that's one possible interpretation. So say don't take the formulas of quantum mechanics seriously at any level, at the level of the atom or at the level of the cat. At the other end of the spectrum, we have what is sometimes called the many worlds, or Everett Wheeler, or more soberly, as it were, relative state interpretation, which says, well, quite the opposite. Yes, take the formalism of quantum mechanics deadly seriously at all levels. Take it seriously at the level of the atom, take it seriously at the level of the cat. So, yes, indeed, the cat is not definitely dead or alive. Both those possibilities simultaneously exist. Well, then I say, but I've just taken the lid off the box and I'm inspecting the state of this particular cat and she's alive and sitting up and mewing happily. What happened to the bit of the amplitude which described her being dead? Okay? And at that point, the advocates of the many worlds interpretation look you straight in the face and say, well, what you have to realise is that there is actually a parallel universe which is equally real to the one you think you're inhabiting, in which not only is this particular cat dead, but you think she's dead and all your colleagues think she's dead. And then there are all sorts of formal theorems telling you that, in some sense, there can be no crosstalk or interference between these two allegedly parallel universes. Well, I wish I could say something intelligent about the many worlds interpretation, but alas, I fear I can't. And the reason I can't is that, quite literally, I do not understand it. I mean those words quite literally. I do not understand it. When the advocates of the many worlds interpretation tell you that these parallel universes, of which I have no experience and could in principle never have any experience, they say these are, quote, equally real, unquote. I mean, those words sound like English. What do they actually mean? To me, they mean absolutely nothing. And so, I mean, now I'm going to offend at least some people in the audience, I'm sure, at this point, but I seriously think that in the year, 2200, when historians of science come to write the history of this period, they'll be amazed that so many otherwise intelligent physicists could take this kind of nonsense seriously. I really do. So, finally, we come to what I call the Orthodox Resolution, and the reason I call it the Orthodox Resolution is that I think it's the kind of resolution which a lot of practicing physicists come to more or less spontaneously once they start thinking seriously about these problems. You recall that, in general, the probability for B or C, when paths B or C were open, is not simply the sum of the probabilities for each path separately, but also had this famous interference term. However, hopefully you also recall that if A sub B is equal to A plus or minus A sub C at random, then the interference term averages to 0, and you get back to the common sense result. Now, it's a rather general observation, which I would tend to agree with, that generally speaking, if you don't take very special precautions, the effect of the outside world does tend to be to randomize this sign. And that effect becomes stronger as the system gets larger and more complicated. So that's something which I, generally speaking, would agree with. That's true. And therefore, the interference term vanishes by the time you've got up to the level of everyday objects, like cats. Technically, the word for this phenomenon is decoherence. So far, so good. I don't disagree with the argument up to that point. But now, here comes the crunch. It says that since now the result is the common sense result, which is precisely the result you would have got had you assumed that each system chooses either B or C, therefore you can legitimately say each system chooses either B or C. And personally, I think that's a gross logical non sequitur. It confuses the possible interpretations of the quantum formalism with the evidence that one or other of these interpretations is or is not valid. At the microscopic level, we believe that we could not interpret a quantum superposition of A sub B and A sub C as saying that each system chooses one alternative or the other. The evidence that we could not do that is the phenomenon of interference. Now, by the time we get up from the level of atoms to the level of cats, for sure, the possibility of observing the interference has gone away. That is, the evidence has gone away. Nothing, however, has changed in the formalism of quantum mechanics. So, it's exactly the same as it was at the microscopic level. So simply because the evidence against a particular interpretation has gone away, does that mean we are free to embrace it? I think that's a bit like the following. Suppose we have a murder trial, and there's the accused, let us say, is accused of having hacked his wife to death. And there is a vital piece of evidence, which is, say, an axe with her blood all over it and his fingerprints all over it, etc., etc. Everyone says for sure he's guilty. Now suppose that for some reason, mysteriously, halfway through the trial, that vital piece of evidence mysteriously disappears. Does that mean the accused has suddenly become innocent? I don't believe it does. Similarly, I don't believe that the fact that the evidence against a particular interpretation has gone away means that we are now suddenly free to embrace it. So, personally, I can't regard any of these three interpretations as satisfactory. So what next? Well, what of course, what we've so far left out is the possibility of assuming that, in fact, quantum mechanics is not the whole truth about the physical universe. That at some point on the route from the atom to the cat or to our own direct perceptions, the quantum mechanical description breaks down and is replaced by something else. Now, I won't say for the moment what else, but you say, okay, fine, it seems a not totally unreasonable idea, but do you have any specific examples of alternative theories? And the answer is yes. There are actually quite a few of them floating around, some better developed than others. The best developed alternative theory to quantum mechanics at the macroscopic level is the so-called GRWP, that's these people down here, theory. And basically in that theory, what you have is a universal noise background which is not itself quantum mechanical. That's very crucial. It's not itself quantum mechanical. That, by a term in the equations which is not there in standard quantum mechanics, that noise induces a continuous stochastic evolution to one or other of the two states of a superposition. The trigger for this reduction is basically the separation of the centre of mass of some number n of particles in the two states you're considering. What's very natural, very nice, and comes out very naturally in the GRWP theory, is that the rate of evolution to one state or the other is proportional to the number of particles which are behaving differently in the two states. So that has the following result. Imagine that you have, say, a photon coming from the most distant galaxy that we can currently see in the universe. That photon has been en route for something like 1 billion years. But it's only one particle. Therefore, its rate of collapse into one state or the other is extremely slow. So slow that it gets to Earth. I can put it through the two arms of a Michelson interferometer and observe interference between those two parts, just as quantum mechanics says. In other words, that photon is, to all intents and purposes, going to behave exactly as quantum mechanics says with no corrections. On the other hand, what about Schrodinger's cat? Well, certainly many, many atoms behaving very differently depending on whether she's alive or whether she's dead. Okay? In one case she's sitting up straight, and the other she's slumped over on the floor. So there certainly is a major displacement of the centre of mass of a very large number of particles there. As a result, the triggering process is much, much faster and could easily take place on a time scale short compared to the scale of human observation. And let me emphasise, that's not, as it were, put in by hand into the GRWP theory. It does follow from the basic postulates. Finally, a final property which any reasonable competing theory has got to have is that in a typical measurement situation, all the statistical predictions of such a theory are identical to those of standard quantum mechanics, and indeed that is the case of the GRWP theory. That's one specific alternative theory. There are various others around. For example, Roger Penrose has developed a theory based on the special effects of gravity and general relativity. I'm not going to plant my flag on any particular one of these alternative theories, but I would like to consider a general class of theories which I will call macrorealism or macrorealistic, which have the property that at any given time an object, a everyday level, a macroscopic object, which has available to it two macroscopically distinct states, for example, like states of this water bottle here or here, such an object has at all times definitely to be in one state or the other. It is not in a... thank you. Thank you. Yes, maybe necessary. It is not in some kind of weird quantum superposition. Something else has taken over. We don't know what, but something else has taken over. Well, okay. Given that, then the obvious question is, which is right, is quantum mechanics in fact the whole truth? How would we tell? And now there's a very obvious consideration that comes in. If in fact all everyday scale bodies have the property that the interference term is randomised by the so-called decoherence effect, then we will always get the common sense result. In other words, all experimental results, as predicted by quantum mechanics, will be just as if one path or the other were followed. So then, under those conditions, there's really no way of telling whether quantum mechanics is the whole truth or not, since it simply predicts the common sense results. So what we must do, what we must try to do, is to find some everyday scale object where decoherence is not effective. In other words, I don't randomize the sign of those two amplitudes in the way that we previously did. The question is, does any such exist? Now, when I and a few other people started, as it were, arguing in favour of this kind of program way back around 1980, we got a lot of flack from the professional quantum measurement community, who told us this, you're quite nuts. Everyone knows that by the time you get to the scale of everyday objects, decoherence is always going to kill you stone dead. Well, they've had to eat their words, basically, as we'll see. It turns out, in fact, quite a number of objects which are, well, I mean, they're not at the level of cats, but they're getting there, as we'll see. There are quite a number of objects where, which are surprisingly macroscopic, where decoherence is not effective. What we need for any kind of reasonable experiment is, first of all, that the difference of the two states in question is indeed at the everyday level. Otherwise, really, there's no point in the program. Or not, if not at the everyday level, at something sort of approaching the everyday level at least. Nevertheless, for technical reasons, it turns out that the relevant energies involved in the motion have to be at the atomic level. Now, you might think at first sight that these two requirements were mutually contradictory, but it turns out not at all. There are quite a number of systems, as we'll see, in which they're both satisfied simultaneously. You must have, in order to avoid decoherence, you must have an extreme degree of isolation from the outside world. And moreover, since intrinsic dissipation essentially plays the same role as interference from the outside world, you have to have very low intrinsic dissipation. Well, suppose you find such an object. We'll come in a moment to the kinds of physical system which may be involved, but suppose you've got such a system, what do you do? Well, basically what you try to do is to take quantum mechanics very seriously as regards this object and try to see what quantum mechanics would predict. And of course, it's only interesting if quantum mechanics predicts something other than the common sense result. But as we'll see, in many cases it does. Now, there's a problem here, because the quantum mechanical calculations are actually rather hard. We've got, in real life, as we'll see, the objects in question are not nicely defined microscopic things like single atoms or single photons and so forth. They're nasty macroscopic objects, not quite like this glass of water, but sort of approaching that, as it were, which we don't really even have a detailed microscopic description of them. So it really doesn't make a lot of sense to start from any kind of a priori microscopic description. Instead, what one can do, and this has been, I think, a rather success story over the last 30 years, is that rather than trying to work out a priori what the equations governing the behaviour of the system are, we start from the limit in which quantum mechanics is believed to give the same, essentially, the classical results. There usually is such a limit. And by looking at the system in that limit, we can often deduce enough about the dynamics of the system, or technically about the Hamiltonian of the system, in order to formulate a reasonable quantum mechanical description of it. And this is, as I say, it's actually worked rather well in a number of systems over the last 30 years or so. Okay, so let me. Yes. How long do I have, actually? Because it's now nearly 4:30. Yeah. Well, so, I think I probably need about another 15 minutes. Is that okay? Yes. Okay, good. Okay. So let me just give you a very brief taste of what some of the systems we're talking about actually are like physically. This next viewgraph is courtesy of my Illinois colleague, Dave Van Harlingen, who works on these experimentally. This is an object which is nowadays usually called a flux qubit. It used to be called, in the old days, an RF squid. And basically it's a bit of metal with various wires attached. And the operative bit is actually this rather small region here, which is this one here. And you see that here's the scale, 0.5 millimeters. You would just about see this with the naked eye, but only just. Now, why is this kind of system interesting? Well, It's interesting because it can be made superconducting. So let me just take a very brief digression, just to say a word about the fundamentals of superconductivity as applied to this kind of situation. We believe that elementary particles, subatomic particles, come in two varieties, and they behave very differently depending on whether their so-called spin is even or odd in a particular unit. For those of you who know, this is Planck's constant over 2 pi. If in that unit the spin is integral, then we have so-called bosons. If it's half integral, we have fermions. And these two actually behave in very different ways. Fermions are extremely xenophobic. They will not tolerate more than one particle occupying each individual quantum state. And therefore, at low temperatures, they behave in a very boring way because they basically occupy, if the energy is up this axis here, they basically occupy the states of lowest energy up to a so-called Fermi energy, where the distribution starts to fall off, and after that there's nothing. They're not particularly interesting directly for our purposes. Bosons are much more interesting. They're very gregarious. They love to have lots of particles in the same state. And in fact, they love it so much that below a certain temperature, for a certain density, they will actually put a non-zero fraction of all the particles in a single state. And the number of particles might be 10 to the 23, and nevertheless, they manage to get, say, half of those particles all in the same state. Now, the electrons in metals have spin a half, so they're fermions. But a compound object, consisting of an even number of fermions, has integral spin, and therefore becomes a boson. Example some of you might know about, the helium-4 atom is actually 2 protons, 2 neutrons, and 2 electrons, so an even number of fermions. And that's then a boson. So, and the bosons now can undergo Bose condensation. So we believe that something like that happens in a superconductor. You might think at first sight that what would happen is that the electrons pair off to form bosons, so that you get a tightly bound boson, which is small compared to the distance between them. And so they form a sort of dielectronic molecule. That might be true. Some people believe that something like that is true in the so-called high-temperature superconductors. But generally speaking, at least for the old-fashioned superconductors, we don't believe that's right. Rather, what happens is a phenomenon named as the formation of Cooper pairs. That is, 2 electrons do indeed get paired up, but between them there are any number of other electrons, all making their own pairings and so forth. So people sometimes compare this to a form of modern dance, in which my motion may be correlated to that of my partner, but she is way across the room, and between us there are many other couples, each forming their own correlations and so forth. It's a very strongly collective, correlated state. Now, in the simplest theory, which is due to my colleagues Bardeen, Cooper and Schrieffer at the University of Illinois in 1957, the simplest theory, once the Cooper pairs are formed, they must automatically undergo Bose condensation. It's not an option, they must do it. And therefore, they must all do exactly the same thing at the same time. And that must be true also in non-equilibrium situations. So now let's look at a simple application of this. Suppose we have a superconducting ring in an external magnetic flux. This is a bit technical, so don't worry if those of you who don't follow this in detail. Turns out there's a quantization condition for a particle of charge 2e, that is a Cooper pair. That is a particular quantity called the circulation is given by this. This is just a collection of fundamental constants. And then you have an integer minus the flux through the ring in units of the so-called flux quantum, h over 2e. Now, if phi is 0, then the energy is proportional to k squared, not to k. That's an important point. Now, if phi is 0, then the unique lowest energy state must have n equals 0. So that all the pairs are at rest, and that's very boring. Nothing particularly special is going on. However, if phi is half a flux quantum, then the ground state is what we call doubly degenerate. That is, there are 2 possible states which have the same energy corresponding to n equals 0 and n equals 1. You can easily work out that the energy is the same in those 2 cases. So in other words, there are 2 possible states. Either all the pairs are rotating clockwise or they're all rotating anti-clockwise. Now, what you might say, well, wait a moment, can't I have 50% rotating clockwise and 50% anti-clockwise? And the answer is no. Turns out, for technical reasons, that's very strongly forbidden by energy considerations. or more generally, it's forbidden by the statement that all the electrons, all the Cooper pairs must be doing the same thing. Okay, so either one. So classically, as it were, either you get one state or the other. Now here comes the crunch. Suppose we actually pretty this up a little and put in a so-called Josephson junction in our bulk superconducting ring. If you don't know what a Josephson junction is, think of it as a sort of gate which will allow the pairs to pass but with increased difficulty. Then it turns out that, according to quantum mechanics at least, we might be able to actually generate a state which is a quantum superposition of all going one way and all going the other. And in each case, the currents are not insubstantial. They're something like 1 microamp or so. So it's not, whether that's everyday level or not, maybe as a matter of definition or taste, but it's not tiny anyway. And, well, the question is, now, could we actually verify experimentally, or alternatively falsify that this is happening? And the earliest experiments were spectroscopic in nature. Crudely speaking, if you believe that at all times the ring is either doing one thing or the other, then the energy levels are given by this PEC line, and by spectroscopy you actually measure the difference between these energy levels. So you could actually tell. If, on the other hand, you actually have this quantum superposition, then some of you may know there's a sort of, those of you who know about such things will know there's a sort of level repulsion effect, and that means that the energy levels are not given by the PEC curves but by the green curves. So it's very characteristic of having this superposition here. And again, by spectroscopy we measure this. And sure enough, the experiments were done about a dozen years ago now in 2 places, and they indeed showed that reasonably satisfactorily that you got the green curves and not the PEC curves. So it does look as if this kind of quantum superposition does exist, or at least everything is consistent with it existing. More recently, there have been some spectacular real-time oscillations. Those of you who know about the ammonia molecule may remember that, crudely speaking, you can start the ammonia molecule with the nitrogen to the left of the hydrogen triangle, and then if you measure where it is subsequently and take a histogram, you'll find that histogram oscillates. And again, that's very characteristic of having a superposition and not just one of the states or the other at intermediate times. And again, these experiments have been done just to show you that the real data exists. Oh, I don't even have this view graph, so it doesn't matter. But these experiments have been done, and these oscillations are actually remarkably stable. If you'd asked me to predict in say, 1999, before any of these experiments were done, how many oscillations you were going to be able to see before it was damped out experimentally, I'd have said, well, you'd be lucky if you see 2 or 3. In fact, people see now 500 or more. So it's really quite spectacular. It's almost an example of Murphy's Law in reverse. Things work a lot better than they're any right to. Well, okay, so where are we? There are other experiments where quantum mechanics has been tested in the general direction of the everyday world. Very nice series of experiments in Vienna on free space molecular diffraction. These are, for those who know about the microscopic Young-Slitz experiment, these basically are Young-Slitz experiments, but done now not with single electrons or even with single hydrogen molecules. I don't know if anyone knows this. It's an interesting historical fact. The first Young-Slitz experiments, or Young-Slitz-like experiments on hydrogen molecules were actually done ages ago, way back in 1928. But now these are huge advance about these. These are carbon-60 or carbon-70, something like 1,200 elementary particles behaving differently in the 2 branches of your superposition and still showing the typical interference effects. Again, been experiments on magnetic biomolecules. If the raw interpretation of the raw data given by the authors is correct, then the number of particles which are behaving differently in the 2 branches is now something like 5,000. Very nice experiments on quantum optical systems where it's something like 1 million. But I think the Guinness Book of Records is taken by the superconducting systems that I was just talking about, where you've got something like, in the 2 branches of your supposed superposition, something like 10 to the 10 particles are, well, whether they're behaving differently or not is to some extent a matter of definition, and some argument about that, but certainly a very large number are behaving differently. Well, okay, so that's where we are right now. Quantum mechanics everything seems consistent with quantum mechanics working at the scale of these superconducting devices. In other words, you can have as many as 10 billion microscopic particles behaving quite differently in the two branches of the superposition. You still see the interference, and that then is rather strong indication that you do indeed, that the system is not doing one thing or the other, but somehow managing to do both at the same time, or neither. Where do we go from here? First, most obvious application is to larger or more complex objects. For example, people are now thinking of scaling up the Vienna molecular diffraction experiments to the point where they may be able to deal with, they've already dealt with small biological molecules. They may be able to deal with, say, myoglobin, eventually a small virus, and in fact, if Marcus Arndt and Anton Seilinger continue along the lines they're going, someday they might even be able to diffract their most obnoxious graduate student through this apparatus and see if it works or not. Not totally absurd. However, I don't think that in itself would be particularly interesting, because after all, in all these cases, one's really talking about a rather crude superposition of the centre of mass of the molecule or whatever. And I don't think there's any particular reason to believe that the centre of mass of a graduate student will behave any differently from the centre of mass of a large molecule. So that perhaps is not the most interesting direction to go. A more interesting direction is superpositions of states of different biological functionality. Now, it's generally believed that the first stage of the human visual process involves the triggering of a conformational transition in the rhodopsin molecules in the retina of the human eye. Exactly how many photons are needed to trigger that is a matter of some dispute in the psychophysics community, but certainly I think most people are agreed that half a dozen will do it. Now, in principle, there's nothing particularly difficult about preparing a quantum superposition of no photons and 6 photons. So now you shine that on the human eye, and at least in principle, you would expect to get a quantum superposition of a triggered and untriggered state of your rhodopsin molecule. Now, of course, the moment that you suggest to any practicing biologist an experiment of this type, they'll sort of look at you like you're quite nuts and tell you this is total nonsense, because everyone knows that biological systems are warm and wet. And when the biologists say warm and wet, you take your dictionary and translate that into the language of physics, and it means huge amounts of decoherence. So in other words, the system, almost certainly you're just going to get the common sense result. Nevertheless, someday in the not so distant future, I suspect that those experiments are going to be done. In the meantime, we actually at the University of Illinois, my colleagues Paul Kwiat and Francis Wong and myself we actually have a grant from the Templeton Foundation. We're just taking the first tiny step along this path. We're actually doing an experiment to see if if a conscious human observer reacts to quantum superpositions in the same way as an inanimate detector. Oddly enough, that experiment never seems to have been done previously, and we're going to do it. Of course, I think it's about 1 chance in a million it's going to give an unexpected result, and if it does, we're going to spend the rest of our lives defending ourselves against the obvious sources of error. But never mind, it's a start. Finally, and this is the last part of it, it really is the last few minutes of my talk, direct tests of macro-realism. What do I mean there? What we've managed to show so far is that at the level, say, of superconducting devices, everything is consistent with the assumption that quantum mechanics is still working. But I'm a Popperian in my philosophy of science. I believe that no finite number of experiments could ever show unambiguously that a particular theory, in this case quantum mechanics, is right. What we may be able to show, with some qualifications, is that with a finite number of experiments, we may be able to prove a class of theories wrong. So I'm a falsificationist. Right? So what class of theories are we going to try to prove is wrong, or maybe not prove? Well, let's consider the general class of macro-realistic theories, and the way it works is something like this. Let's do it specifically for a squid, a flux qubit, the kind of superconducting device I was talking about. Let's define the class of macro-realistic theories by a set of postulates. First of all, the system is always in either the plus state or the minus state, two states in question, whether or not it's observed. We know that whenever we observe it, it always does turn out to be one of these states or the other, with a very tiny fraction of results somewhere in between. So let's assume, we'll put that tiny fraction aside and assume that the first assumption then is whether or not we're observing it, it always definitely is in one state or the other. That, of course, is not what quantum mechanics says. We're assuming something different. Now, it turns out that by itself is apparently not susceptible to experimental tests, so we've got to supplement it. We'll supplement it with two postulates: induction, which, crudely speaking, and this is my shorthand, it's not really a correct use of the term, I think, but it really means the conventional error of time. That is, that the state of a system can be affected by what happened in the past, but not by what's going to happen in the future. So that's, I think, fairly straight, cut and dried. The third postulate is what I call non-invasive measurability, which means that I can, in principle, determine whether the plus or minus state is realised without any effect on the subsequent behaviour or on the state itself. Crudely speaking, that works in the following way. Suppose that I believe this water bottle can either be here or here. What I'm going to do is I'm going to shine a flashlight here. If I see the bottle, then, of course, I can argue that I might have affected it by shining a flashlight. So I'm going to throw that one away. If I don't see it, then I can reasonably infer that it's over here, and moreover, since I only shone my flashlight here, I couldn't have affected it, right? And if you now tell me that despite the fact it really was here, I nevertheless affected it by shining my flashlight here, then I have to ask you what you really mean by saying it's over here in the first place. I don't think it makes a lot of sense. Now, remember, that is not a quantum mechanical assumption. But it's a very natural corollary of the assumption of macro-realism, I believe. So, given all those, it turns out there's a certain quantity, let's call it K, whose value can be directly inferred from an appropriate series of measurements. And now we have some predictions for K. Turns out that any macro-realistic theory will predict that K is less than or equal to 2. Those of you who are familiar with Bell's theorem may realise this is just a transcription, in effect, of Bell's theorem to a different kind of context. So and I think that's usually agreed, and there's not much doubt about that assumption, that conclusion. Again, not much argument that if you apply quantum mechanics and assume that your system is ideal, then K comes out to be 2.8, which is obviously not less than or equal to 2. Finally, quantum mechanics with all the real-life complications, well, we've done a fair amount of work on that, both theoretically and experimentally, over the last 30 years. And I think it's probably fair to say that most people agree that under reasonable experimental conditions, quantum mechanics will predict that K is not as large as 2.8, but still larger than 2, and therefore still in contradiction with this. But this is the most delicate part of the argument. So, to the extent that the analysis of C within quantum mechanics is reliable, we can actually force nature to choose between macro-realism and quantum mechanics. And those experiments have not yet been done, or at least to my mind not been done under the appropriate conditions, but I think they will be done very likely in the next 5 or 10 years, probably in the next 5 years actually. And here are the possible outcomes, or some possible outcomes. Most disappointing outcome is that the experiment doesn't work. In other words, once we come to actually do it in real life with a specific system, we will find that there's too much noise around, which we hadn't bargained for, so that too much decoherence, so that the quantum mechanical prediction comes out to be consistent with the macro-realistic one. Well, that would be disappointing, but I'm sufficiently confident in the skills of my experimental colleagues to believe that they'll rather soon figure out ways of reducing the noise to the point where this is no longer a problem. Second possibility, K comes out to be greater than 2, which would imply, I think, and I think most people would agree with this conclusion, that would imply that at the level of the experiment, in this case at the level of superconducting devices, macro-realism is definitively refuted. Whereupon 99% of the physics community will turn around and say, big deal. I could have told you that without spending $500,000 on the experiment. I mean, after all, we all know that quantum mechanics is the whole truth about the physical world, so why would your experiment be any different? Well, fair enough, but at least one would have brought up the Schrodinger's Cat paradox from the level of single atoms or pairs of atoms, which is where it had lain for 80 years or so, up to a level which is okay. How far is this? Is the level of superconducting devices along the road from the atom to the cat? Well, in physics, if you want to make your results or your progress look good, you plot it on a logarithmic scale. So on a logarithmic scale, the superconducting devices are something like 40 or 50% along the road to the macroscopic world. And in fact, actually, there is a not totally trivial argument that says that, in some sense, they're already there, that there are experiments which most people would regard as it were, at the everyday level, which are at the same level as those superconducting devices. So I think it's not trivial if this does come out. Finally, of course, there's the possibility that it turns out that K is less than 2, and the naive conclusion from that would be that we have now refuted at the level of the superconducting device or whatever, quantum mechanics. Is the physics community going to draw that conclusion? Not in your life. At that point, 99.999% of the physics community is going to turn around and say, must be a bad experiment. Why? Well, we all know that quantum mechanics is the whole truth about the physical world, so if your experiment says different, too bad for your experiment. Let's just suppose that that experiment is redone in 6 different laboratories, 6 different parallels of longitude under 6 different political systems and funded by 6 different funding agencies, and it still comes out that K is less than 2. Well, what then? Then, of course, the roof falls in on the theory. All the people from atomic physics, particle physics, cosmology and whatever, who are used to dealing with these nice, cleanly defined microscopic objects, which are always the same. You know, every sodium atom is the same as every other sodium atom. There's no doubt about it, okay? All these people will come in and say, you guys in condensed matter physics, that's me, you guys are just too naive for words. You've got this messy bit of metal sitting there on your lab bench. You can't even tell me its exact chemical composition, let alone where all the dislocations and whatever are. It's interacting like mad with the vibrations of the lab bench, with the black body radiation field. It's just a mess. How could you ever be so arrogant as to conclude that if your theory, your application or your alleged application of quantum mechanics fails to agree with the experiment, the problem is with quantum mechanics and not with your silly description? Well, fair enough. I think it's a reasonable point. But we have, over the last 30 years, we've tried rather systematically to fight that. And the way we did it, as I said, was by not starting from an a priori microscopic description, but rather working backwards from the classical limit. Let's just, again, because there are still lots of loopholes there. Let's just suppose, for the sake of argument, that all those loopholes are plugged. Everyone now agrees that in the situation of the experiment, quantum mechanics says that K should be greater than 2, and in fact it comes out to be less than 2. What then? Then I think we might have to take rather seriously the following possibility. Over the last 300 years or so, not just in physics, but more generally in the natural sciences, we've tended to rely very heavily on what you might crudely call a reductionist principle. Crudely speaking, what I mean by a reductionist principle is the principle that since big things are made of little things, if you have a theory which brilliantly describes the behaviour of the little things, then it must automatically describe the behaviour, and principle must describe the behaviour of the big things made out of it. In other words, there's nothing extra that comes in at any particular level of size or complexity or whatever. That is not a logical necessity. It's conceivable it might be false. And I think we might have to rather seriously start considering the possibility that it could be false. And if, in other words, that in some very real and literal sense, the whole is more than just the sum of its parts. Let me emphasise, this has nothing to do with an idea which has emerged, has come out as a sort of buzzword in the recent literature, so-called emergence. People who believe in emergence don't believe that quantum mechanics is somehow going to break down at the level of macroscopic bodies. They simply believe that there are, if you like, certain kinds of concepts which are not usefully formulated in microscopic terms. That's a totally different kettle of fish, and much less radical, I think, than the proposal I'm making. So I'm really making suggesting the very radical possibility that there may really be new laws of physics which come in at some level between that of the atom and that of our human experience. And obviously, if that were to be the case, then it would be of interest not just to professional physicists, but certainly to professional philosophers and perhaps even to the ordinary person in the street. So I think you can see from my last few sentences which of these outcomes I'm hoping, and in my heart of hearts, secretly hoping for, but at least while I'm reasonably sober, don't ask me to bet on the results. Thank you.